Nathan Williams is here over Zoom today to give us our second talk. He's from the University of Texas at Dallas, and today he's going to be talking about independent posets.
Okay, thanks so much to the organizers for the invitation to talk. And yeah, I'm a little nervous with all the people in the audience there. You know, there's Curtis Green, Nathan Reading, Bob Proctor, Richard Stanley, Trisha Hirsch, Carl Savage. These people all know the history much better than I do, and I'm going to talk a little bit about history. So if any of you feel the urge to correct me, let's wait until the break. Okay, so right, this is joint work with Hugh Thomas, and it's a nice little gadget that we built out of independent sets. So I need to tell you how we got there, and to do so, I'm going to talk about distance learning. Okay, so we all are involved in distance learning these days, and we've all become sort of experts at it. And we've got a lot of different tools that we can use. Depending on what your university is up to, like my university uses MS Teams, but like for example, we're using Zoom today, so I have to learn how to use that and all that. There's also Google Meet, which is a possibility, and my personal favorite for interacting with students is of course the U.S. Postal Service. That's a perfectly fine mechanism to do distance learning, and then we're doing a comparison between different services. So maybe I want to keep track of various things. For example, is there a free option? Does it offer breakout rooms? What about video support? And last but not least, let me ask the interesting question of has the organization been involved in an antitrust suit? Because that's very important when I'm trying to choose what to use. Okay, so let's think about it. So MS Teams, it has a free version. It offers breakout rooms, video support, and Microsoft was famously involved in an antitrust suit because of bundling Internet Explorer, and this was the whole Netscape war thing. Okay, whatever happened to Netscape anyway? All right, Zoom is a much more recent company. I only started hearing about it since the pandemic. It's got a free version. I assume that we're not using a free version here. It does offer breakout rooms, although we won't be using those for this conference. It has video support, and as it's recent, no antitrust suits yet. Okay, Google Meet. Again, a free version. I don't know how to do breakout rooms, so let me leave that unchecked. It certainly has video support, and Google famously is being involved in antitrust suits right now. So that's kind of cool, antitrust litigation. All right, and finally we come to the U.S. Postal Service, which is, you do have to pay to send your mail. It does not offer breakout rooms or video support. That's either, it's either a problem or a feature. And here's the interesting bit. It actually has been involved in an antitrust suit. This was launched when they changed the standard of weave for mail bags from circular to flat weave. Or maybe it's the other way around, I can't remember. And they were brought to court under the Sherman Act by Flamingo Industries because of this, for this antitrust violation. I went all the way to the Supreme Court where it was thrown out because the Supreme Court ruled that for the function of the, for the Sherman Act, the US Postal Service is not distinct from the US government, and so you cannot, you cannot sue it for antitrust violations. Okay, so this is our setup. And all of this by way of saying that the general context that we're going to have here is we're going to have a set of objects. Those are the services that we were just talking about. And then there are going to be properties, okay? And what I'd like to do is I'd like to have these maps. So I'd like to have this map M, which takes me from an object to the set of properties that it has. So for example, MS Teams has breakout rooms, video, and antitrust. Okay, and conversely, I also have a map J, which takes me from a property to a subset of objects, and it takes me to the objects with that property. For example, antitrust is now returning the Microsoft Teams and the Google Meet. Okay, so far so good. All right, so this is the general setup, objects and properties. And this brings us to Rudolph Willey's formal concept analysis, which is a beautiful marketing job, okay? So what's gonna happen now is we're gonna upgrade this from subsets of objects to shared properties and subsets of properties to common objects, okay? So I'm still aiming to get to independent sets of graphs somehow, but let's continue with our story. Okay, so here's the idea. Let's imagine that I'm just interested in MS Teams and Google Meet. I can say, well, what are the common properties of both of those? So let me sort of define this function M to be the common properties of MS Teams and Google Meet. And it turns out that that's both the video and the antitrust thing, right? So if I look, it's video and antitrust. And conversely, and this is somewhat interesting, if I look at the common objects that have both video and antitrust, then you'll see that it's exactly MS Teams and Google Meet. So this is sort of a pair, where the map applied to this pair, MS Teams and Google Meet, returns the video antitrust. And conversely, if I take the common objects with video antitrust, then I get MS Teams and Google Meet, right? So you could imagine that if I was just restricting, say, to antitrust, then I would return MS Teams and Google Meet. But then if I ask what are the common properties of MS Teams and Google Meet, then I also have to return that video, okay? So interestingly, if I think about this sort of pair where the maps take me from one to the other, then this is supposed to encode a concept, an idea. And the idea here is a big corporation video conferencing software. The big is coming from the fact that it was involved in an antitrust suit, and then the video is keeping track that it provides video conferencing. Lovely. So in general, we'll define a concept to be that. Okay, so the idea is that I have a set of objects, I have a set of properties, and the set of properties are exactly the common properties for all the objects in the set of for all the objects in that set of objects, and the set of objects are the common objects for those objects with the properties in the set Y. So X comma Y. Okay, and the colors are hopefully helping us keep track of everything. Okay. And now what we can do is we can order these concepts. And the way that we can order these concepts is we can just take inclusion of the objects, okay? So for example, over here, this was, I think the Microsoft and Google Meet. This was Microsoft Teams and Google Meet. So the A and the C here, I've dropped the names just for convenience. So this was the A and the C, and the pairing was with video conferencing and antitrust. And so this pair of things, the yellow stuff and the blue stuff, this pair was a concept, and it's sitting right here in this poset of all the concepts, right? So up at down at the very bottom, I have just yellow things. Apparently these are just properties, because you can ask, well, what objects have all properties 1, 2, 3, and 4, that are paid, that have breakout rooms, that have video, and that have also antitrust things. No object has all 4 of those properties, so really there's nothing there, right? It's a pair, and here it's an empty blue set, and then everything on in yellow's properties. And conversely, on the other side, here it's what properties are shared by all of the objects? Well, nothing. So this is really, there's no properties there. Okay. So I'm keeping track of this pair. So this poset is the poset of pairs of objects and properties satisfying this condition, and that to be a concept. Okay, excellent. Any questions so far? All right. Actually, you could order by inclusion of the objects. You could also order by reverse inclusion of the properties. Okay. And the first theorem here, if you were doing formal concept analysis, would be that the poset of concepts is a lattice, and every lattice arises as a poset of concepts. Okay. This is somehow some sort of representation theorem. Yeah, so I can take a lattice and I can represent it in terms of these little grids that I had, or as these subsets as these sets of concepts under inclusion. Okay. So yeah, it's in a lattice, and every lattice arises in this way. So we should talk about what a lattice is. And to do that, let's talk about a little bit about the history of lattices. So here I have a very nice quote from Rhoda, who wrote a survey article about maybe his experiences with lattice theory, called "The Many Lives of Lattice Theory." So I'll read a little bit of this to you, just because it's so interesting. So never in the history of mathematics has a mathematical theory been the object of such vociferous vituperation as lattice theory. He then names some prominent mathematicians who have worked on this, and most prominently Garrett Birkhoff, who contributed a new vision of mathematics, a vision that has been cursed by a conjunction of misunderstandings, resentment, and raw prejudice. Okay, so lattice theory hasn't always had smooth sailing. I'll say a story about von Neumann. Von Neumann apparently was interested in lattice theory, and he was delivering a lecture on it. Well, he was doing infinite lattices, and apparently G.H. Hardy, the number theorist, was in attendance in the audience, and turned to Garrett's father and said. Yes, Margaret, we are. Turned to Berkhof's father, Berkhof, and said, well, he's quite clearly a brilliant man. What's he doing wasting his time on this stuff? So lattices, what is a lattice? So we have a partially ordered set, and we'll call it a lattice if every pair of elements in the lattice have both a join, okay, a least upper bound and a meet, a greatest lower bound. So common examples would be like a Boolean lattice. So just if you take subsets of a finite set, order them by inclusion, then what happens is the join becomes union and the meet becomes intersection. Another example would be fix a positive integer and look at the divisors of that. And now your join will become, your least upper bound will become least common multiple, LCM, and your greatest lower bound will become GCD. All right. So Berkhof, thank you, Nathan, for the yes, exactly. We do need a dictionary for Rhoda's turn of phrase. So Berkhof had high hopes for lattice theory. So you can see. Let me read a little bit of this now. He says, like its elder sister group theory, lattice theory is a fruitful source of abstract concepts, etc. In fact, lattices were originally called dual gruppen, like dual groups, and you could have things like regular representations. And so they really were viewed as a unifying concept for math, at least some people viewed them. And let me just say the final phrase here, though its importance will probably never equal to that of group theory, I do believe that it will achieve a comparable status. And so Garrett Berkhof wrote this in the second edition of lattice theory, and I do not believe that sentence appeared in the third. But lattice theory is making a tremendous comeback. It really is. So what with connections to cluster algebras, what with work on lattices out of, say, Hawaii, really making a big comeback. Connections to representation theory of quivers. So it's really, in combinatorics, definitely coming back, and it has all sorts of applications. Okay, so let's see. I'm still trying to get to independent sets of graphs, and oh boy, do we have a way to go. So let me try to talk about, again, this representation theorem for lattices. So so I want to talk about join irreducibles. So what does it mean to be join irreducible? Well, in our case, you don't need to read this. In our case, all it's going to mean is that there's a unique edge coming out of an element, okay? So let me go ahead and give these names. It'll look a little arbitrary at the moment, but I'm going to try to do this to stay consistent with the example that we had. So I'll label this A. So this is a join irreducible element because it has one edge sticking out from below, right? And then I'll have join irreducibles B, C, and D. Okay, so these are my join irreducibles. These are all of the elements that have exactly one thing sticking out, one edge below. And similarly, a meet irreducible then is going to be an element that has exactly one edge sticking up, okay? And so again, I'm gonna label this in a little bit of a weird way, but it's for consistency with the previous example. So this one will be 1, and then I will label this 2, 3, and 4 like this. So you can see that an element can be both, so again, these are all having one edge up. An element can be both join and meet irreducible, and that's fine. In fact, a lot of these are. Okay, but whatever. Okay, so what's the point here? We're going to use these join and meet irreducibles to give a representation theorem. So let's continue. Okay, so here's the labeling. This is what I just wrote for you, where I computed the things pointing down. So this one was A pointing down, B pointing down, C pointing down in blue, D pointing down. So now the objects are somehow the join irreducibles. The color coding is supposed to make this be keeping track of this. And now what I'm going to define is I'm going to define this J function. And what it's going to do is for an element of the lattice, it's just going to record the join irreducibles that lie below the particular element. So let's do an example. If I take this element 3 in the lattice, whatever, this thing labeled the meet irreducible 3 in the lattice, what I'm going to look at is I'm going to look at all of the join irreducibles that sit below it, and that's going to be my J function. Okay, for this element. Conversely, I can look at all of the meet irreducibles that lie above it, and so for example, there's only one here. Okay, so this is the this is somehow how I'm going to take this element and represent it as this pair of sets. Okay, or for example, this was our example. This was our large corporation video conferencing software. And if I think of the blue stuff that lies below it, it's C and A. And if I think of the yellow stuff that's above it, the meet irreducibles above it, it's 3 and 4. And this is my representation. So I'm recovering the same pictures as before, right? And indeed, that's the theorem. So since any element, it can be written as the join of the joint irreducibles below it and the meet of the meet irreducibles above it. We are in a finite lattice. There's no problems here. Every finite lattice is isomorphic to both or either the J sets under inclusion or the M sets under reverse inclusion. And these are encoding the concepts from before. So this is what we have. So if I keep track now of which, so I'm going to go through and I'm going to keep track this joint irreducible A. Which meet irreducibles does it sit below? 2, 3, and 4. So let me go ahead and record 2, 3, and 4. And conversely, over here, B, what meet irreducibles does it sit below? Well, 2 and 3. 2 and 3. And then I have, say, C, the joint irreducible C, and that sits below 3 and 4. So I put 3 and 4 check marks. And finally, the joint irreducible D, it sits below just 1. Like that, right? And I've recovered my original picture. Okay, the original story that I told you about these services. Wonderful. Any questions? Okay, a few historical notes then. Right, so formal concept analysis was published, this was started out in 1982. It was Rudolf Willey's restructuring of lattice theory. Again, tremendous marketing job, really took off. A lot of conferences, books, tremendous numbers of citations to his paper. However, the similar ideas appeared in the 1973 thesis of George Markowski, who was a student of Birkhoff. And he called this thing the poset of irreducibles. And even before that, in 1965, Marc Barboux had similar ideas. And even before that, Suchin Berger had similar ideas, more of a regular representation. Okay, let me not say more about that. But these ideas have a lot of history to them, and credit is I guess there's plenty to go around. All right. And I want to talk to you, wait, what are we trying to do? We're trying to get to independent sets. Okay, so now I've got these lattices, a very general representation theorem for lattices. What I'd like to do is I'd like to make my way to, I'd like to specialize and specialize and specialize to increasingly nice situations and then generalize. Okay, so right now we're going to be talking about Markowski's extremal lattices. And the reason we're going to do that is because these lattices have really nice representation theorems. Okay, somehow I'm going to be able to make a correspondence between the joint irreducibles and the meet irreducibles, and this is going to let me better visualize what's going on. Okay, so let's see how that works. So here's the same example as before. It's the running example that we're using throughout the talk. And Markowski makes the following definition. He says a lattice is extremal if the number of joint irreducibles is equal to the number of meet irreducibles is equal to the length of the lattice. So by the length of the lattice, what I mean is it's the length of the longest chain. So for example, in this one, there are 4 joint irreducibles. There are 4 meet irreducibles, as we've computed. And the length of the longest chain, well, there are actually 2 maximal chains. And the length is 1, 2, 3, 4 for both of them. Okay, so indeed, in this case, it's 4. All right, so this is his definition of extremal. Why make such a definition? Okay, and the reason is because you're going to be able to pair up the joint and the meet irreducibles in the following way. So what we're going to do is choose some maximal path. So in this case, I'm choosing this maximal path, okay? This maximal chain. And I'm going to imagine trying to build this chain by starting at the very bottom and then joining with joint irreducibles. So for example, from the bottom element, to move up this edge, I must join with the joint irreducible A. So I'll label this edge by an A in blue. Okay? Now, if I try to follow this edge up, I have to join with the joint irreducible B. So I'll label this by B. If I try to go up this edge, then I need to use the joint irreducible C. Can you see that? Because the joint of this and this give me this element. Okay, so I get to label this by C. And finally, if I try to move from this element to the top element, then I need to use the joint irreducible D in order to go up. And so what happens is that every single edge in in this maximal chain gets labeled by a joint irreducible. But we can play the same game going down. And so let's do that. So now I'm going to start at the top, and I'm going to start meeting with meet irreducibles and see what happens. So I start here, and to get down, it looks like I need to take the meet irreducible 3. And now if I'm trying to go from this element to this element, then I need to meet with the meet irreducible 2. I do hope this is making sense. And now if I'm trying to go from here to here, then I need to meet with 4, because the meet of this guy and this guy is this guy. I'm trying to go down this chain systematically by meeting with meet irreducibles in the same way. So I get a 4 here. And finally, if I'm trying to get from this element to the bottom element, then I have to meet with the meet irreducible 1. And so I get this label. So I get a label of the steps in this maximal length chain by both join and meet irreducibles. Okay, that's the point. And well, what does this let me do? Well, let's take a look. What I'm going to be allowed to do now is I'm going to be allowed to sort of merge my my table here. This table is going to get a nice visual representation. So the idea here is that let me keep track. So I've kept track of what properties things don't have, and let me draw edges. Okay, so I have the objects down here, A, B, C, and D. I have the properties 4, 2, and 3. Okay, the reason I've paired them up like that is because B is getting paired up with 4 from our previous calculation, right? B got paired up with 4. And C got paired up with 2, D got paired up with 3, A got paired up with 1. So I've written down this pairing right here. And now I've placed the meet irreducibles above the joint irreducibles like this. And I'm just going to draw the edges that don't exist. So A goes to 1, okay? And B is connected to both 1 and to 4, okay? C is connected to both 1, like that, and to 2. And D is connected to 3, it's connected to 4, and it's connected to 2, like that. Okay, so now what I want to imagine doing is I want to imagine shrinking the distance between 3 and D, shrinking the distance between 2 and C. So 3 and D, 2 and C, B and 4, I want to shrink them, and A and 1, I want to shrink them onto each other, okay? And I want to draw these same edges, these same directed edges. So for example, D, we just computed, was connected to 2, 3, and 4. So 2, 3 is itself, so let me not draw that edge, and then to 4, okay? Conversely, if I look at C, C was connected to 1 and 2, so let me draw the edges. So 1 and then 2 is itself, so let me not draw that. And then B was connected over here to 1 and 4. So 4 is itself, let me not draw it, but down to 1. And then A was just connected to 1, which was merged onto each other. Okay, so I get this nice graph coming out. All right, this is the point. I'm trying to come up with a beautiful representation theorem. That's why I'm doing this. And now let me see what happens. If you think hard about maybe what these concepts were in terms of this new directed graph, what happens is what you're trying to do is you're taking this graph, and if you're looking at the nodes, you're allowed to color them one of 2 colors, either blue or yellow, subject to the conditions that you can't be both blue and yellow. No node can be both blue and yellow. You can't have a blue pointing to a yellow, and the blue and the yellow are maximal with respect to the first 2 conditions. Lovely. And if you do this, then the previous post set of concepts or lattice of concepts gets redrawn in this pretty little way. Okay, it's just blues and yellows and there's some whites, right? So let me show you. So for example, this one is interesting because if I color this blue and this yellow, okay, that seems fine. I can't make this blue because then a blue would point to a yellow. And I can't make it yellow because then a blue would point to a yellow. So this is in fact, this satisfies the conditions to be a maximal orthogonal pair, which is I've colored things blue and yellow. Not all of them had to get a color. Not all of the nodes had to get a color, but blue can't point to yellow, and I sort of have colored as much as I can. Okay, these are the concepts again. Here's our familiar concept of big corporation video conferencing software. Okay, in the same place as before. Now it's just beautifully represented though. And if you know something about Birkhoff's theorem for distributive lattices, okay, then this guy looks funny to you, right? And the way that I get rid of him is I could change the condition. If I could send mail for free, okay? If I think about what that would do in terms of this, that would change this to an X. So now D would point to 1, and so I'd have this point D pointing to 1. I'd get this extra edge here, okay? And this extra edge then would invalidate this because now a blue would point to a yellow, right? So it disappears. When I change so that I can send free mail, it disappears. And I'm left with the lattice of order ideals of a distributive lattice. Okay, so this is a generalization of the theorem of distributive lattices to extremal lattices. And let me say just a quick word more about that. So the right way to think about extremal lattices, so here is a particular graph, G, okay? It's a directed acyclic graph. And if you thought about what the lattice of order ideals of this as a poset would be, like if I made the comparability graph of this, then you'd see this sort of spine. What I've drawn here is I've drawn the entire extremal lattice, but sitting inside of it is the distributive lattice, and then there's all sorts of other stuff around. Okay, so it's somehow a more general notion. And if I were to add in all the edges that I was supposed to make this a comparability graph of a poset, then I'd recover just this spine here, these maximal chains. Okay. Awesome. Okay, we're still not to anti-chains. Okay, so we have, not anti-chains, but to independent sets. So we still have a little ways to go. And the problem is that we just haven't gotten to the nice enough lattice yet. So this brings us to Hugh Thomas's trim lattices, okay? So trim, so Hugh was motivated by a different question. And his question was to ask, what if a distributive lattice weren't graded? What would happen then? Like what kind of object would you have? So let me not give his original definition, which was in terms of left modularity. Let me instead give the definition, an equivalent definition, which is really a theorem that we came up with. Okay, so I'm going to be given an extremal lattice. All right, so as an extremal lattice, I have this representation in terms of these this directed acyclic graph with colorings blue and yellow. And now I want to look at any relation. So I've got the blue set and the yellow set for the lower guy. I've got the blue set and the yellow set for the guy above it, right? And I call it overlapping if the yellow set of the guy below intersect the blue set of the guy above is not equal is not empty. Okay, so for example, let's just look at this edge right here. So what I'm supposed to do is I'm supposed to look at the yellow stuff here and intersect it with the blue stuff there. So the yellow stuff here is these two, and the blue stuff here is these two, and there is an intersection of 4. Does that make sense? But what's interesting is this guy right here and this guy right here, if I look at the yellow stuff below and the blue stuff above, the intersection is empty. So this is not overlapping. This relation is not overlapping. Okay, this was an extremal lattice, but it doesn't satisfy this overlapping condition. The blue stuff above has 0 intersection, has empty intersection with the yellow stuff below. Okay? So the theorem / definition for this talk is that an extremal lattice is going to be called trim if and only if every relation is overlapping and if and only if every cover relation is overlapping. So what does this let us do? What's the whole point of this? The whole point is that before, in an extremal lattice, what we knew how to do was label the maximal chains in the extremal lattice, right? That was the whole point of an extremal lattice, is that you could label the edges of a maximal chain by the joint and meet irreducibles. The fact that every relation is overlapping is going to let us label every edge now of the trim lattice. So let me show you here. So let me write down the labeling. I'm doing A, B, this was D, and C like this. This is my graph. And now let's take a look. So for example, this guy intersects this. The yellow intersects the blue here in A. So I'm going to label this edge by an A, right? And then like if I look at this guy to this guy, if I'm trying to label this edge, then I look at the yellow here and the blue here, and it intersects here, which is B. So I'll label this with a B. And similarly, this will be C, and this will be D, and this will be B, and this will be C. Let me just do this one right here for you. So if I look at the yellow underneath and the blue above, then there's a single intersection, and that gives me the unique labeling D. It's this D right here. Yeah, and similarly, if I look at the blue here and the yellow here, then this guy has to be labeled by A. Interesting. Okay, so the whole point of a trim lattice, I guess, is that now not only do I get to label the maximal chains, as in an extremal lattice, but I get to label every single cover relation, every single edge in the graph. Okay, and this is going to give us a new way to represent the elements in there. See, the point is that if I look at the labels that are pointing down. Okay, so let me write the labels again. So this was A, B, C, and D. This was B. This was C. This was D, and this was A. If you look at the labels that are pointing down, for example, D and A point out, and I just record those values, that uniquely characterizes the element inside of the trim lattice. And in fact, it turns out that they're going to be exactly the independent sets of the underlying acyclic directed graph. So for example, here, this element is uniquely characterized by the fact that it just has a single edge pointing out of it, down out of it, which is D. And I get every single independent set in this way. I don't get every single graph in this way, but I get every single independent set of particular graphs when the Markowski's graph representation of the extremal lattice happens to be trim. Okay, so we actually have gotten to independent sets of a graph, and not a moment too soon, as I have about 10 minutes left, and I still have to tell you about independence posets. So that's where we are now. And now what we're going to do, so Hugh Thomas asked, what if a distributive lattice weren't graded? And now we're going to ask, what if a distributive lattice weren't a lattice? Okay, so let's see how we do this. The idea is, so for a trim lattice, the elements were characterized by, say, the labels of the edges pointing down or the labels of the edges pointing up. And in particular, the elements were actually independent sets of the graph. So what this suggests is that if we can properly understand how these guys fit together, so this D map, right, is going to be an independent set of the graph. This U map is going to be an independent set of the underlying graph. How do they fit together? And how can we express the cover relation, right? So we can study the trim lattices where we know that we have this representation, and we can see how it actually behaves in terms of just these independent sets, these pairs of independent sets. What are they? Can we characterize it? And we can, it turns out. So here's our definition. So we're going to have a pair. So you should imagine you're starting with a directed acyclic graph, finite, and we're going to be coloring some of the nodes blue and some of them yellow, as before, okay? But now the blue nodes are going to be an independent set. The yellow nodes are also going to be a different independent set, okay? And I want to have them, I want to have no blue, I can't color something both blue and yellow. And also I don't want to have any arrows from blue to yellow. So far it's the same thing as what we saw before. But now I'm gonna say that, so these independent sets are going to be tight if, okay, so now whenever I can increase an element of D, so let's imagine that this was filled in, okay? Now what I mean by increase is move backwards along an arrow. So this thing can actually be increased while still being an orthogonal, There's no blue pointing to yellow. So that could actually be increased. So this example, and in fact, it could be increased even further in this case. So this is not, this was an example of something that was not tight. I'm going to show you. And now, for example, if I have an element of U is decreased, that means moving along this edge. Well, this is not tight either because this yellow can actually move down to here, and even further, it could move down to say here. And that would be perfectly legitimate. So it still is orthogonal if I do this. So this is not tight. Again, I'm showing you what's not tight. Now, also, I want to have things. I want to not be able to add any element to D. So, for example, if I'm over here and I try to add a blue thing, I can add a blue right there. And it still satisfies all the conditions to be orthogonal. So there's no blue pointing to yellow. There's nothing that's both blue and yellow, and everything's still an independent set. And I can't add anything to yellow. That's the last point here. And here I could add here. Okay. So this is the condition. This is somehow the condition for this down and this up to actually be this nestled pair of independent sets. And we're thinking of them as, I have some value x in the lattice, and then there's stuff pointing up, that's the U. There's stuff pointing down, that's the down set. And this is the condition. This is actually the condition. We've written down the condition for when this happens. How can you have the down set? What does the corresponding upset say? Okay, so let me show you how to actually, if I give you the down set, let me show you how to construct the upset. So the idea here is I've fixed an independent set I, and it's the same independent set in both sides. Here and here, it's the same independent set. All that's changed is the color. So over here, I'm thinking of it as the blue part. It's going to be blue, and over here, I'm thinking of it as the yellow part. The edge is sticking up. Okay, I want to show you how to complete it to the unique thing that satisfies these nasty conditions that I was trying to explain to you. Okay, and it's really quite simple. You greedily complete. So what I want to do is for yellow, I want to sort of float upward, and I'm going to look to see as I move up this graph if I can add yellow, and I want to greedily do so if I can. So let me show you. So for example, can I add this guy? I cannot, because that would be a blue pointing to a yellow. So don't do that. But I could add here. I can't add here. I can't add here because this guy is already blue, and I can't have something that's both blue and yellow. I can't add here because I've already colored something yellow here. I can't add here. I can add here though. Let's see. I could add here, and then I can't add there or there because blue would point to yellow. I can't add here because then yellow would point to yellow. It's not an independent set. Continuing. I can't add here. I can't add here. I can't add here because of this. I can't add here because of this. Okay. I can't add here. I can't add here. I can't add here. I guess this guy can make yellow, and this one I can make yellow, and that's it. I think that's right. You with me? More or less. Okay. And conversely, if I'm trying to go the other way, then I flow down from the top. Okay, so blues have to flow down, and this is going to be the unique thing, right? So somehow, the condition that D being increased and U being increased is telling me what order I have to do things. And this is where I need the acyclic thing. And this is where probably I've lost so many people because it got kind of technical. But the point is, we're just trying to build this weird little structure. But okay, so can I add this in? I can. I can't add. I can't add. I can't add. No. No. Yes. I can add there. And conversely, no. Yes. And then I can add here. I can add here. Okay, this will all be over soon. I promise. I apologize. It looked so much better when I thought about doing it. Okay, and then this guy right here. Okay, so I think this is how you complete these sets, and yeah, okay, that's what I'm going with. So I flowed upward to make the yellow, I flowed down to make the blue, and this was unique, and it was greedy, and so somehow this is the unique way to do it. Okay, so this is the way to pair up and downs, and these are somehow telling me the edges up. These are telling me the edges down. The blue stuff tells me the edges down. The yellow stuff tells me the edges up, and I want to tell you how to make cover relations now, right? There were sort of two things that we were trying to do. One was, how do D and U fit together? We did that. Now we want to express the cover relations, okay? So our model here is we're looking very hard at trim lattices, but now we're sort of saying, can we generalize it even if the thing weren't going to be a lattice, okay? And yes, we can. So here's what we're going to do. I'm going to show you how to flip at this element G, okay? So the first thing you want to do is you want to change the color. So G was orange, so I'm going to change it to blue, okay? Now, I want to sort of differentiate between the stuff that's above G, the stuff that's below G, and the stuff that's incomparable to G. All right, so everything that is incomparable to G is going to be preserved. So for example, these two blue guys, let me actually draw it here, right? So everything that's over here is going to get preserved. Everything that's over here is going to get preserved. And here we are, perfect. And now, what I want to imagine doing is I want to imagine flowing up out of G, which means I'm going to be changing the yellow set. So the blue set stays fixed above G, okay? And then I want to imagine flowing down out of G, which means that the orange set is going to be fixed below G, like so. And now I'm just going to uniquely complete in the way that we've sort of specified. So I'm going to flow up and just add oranges when I can. So I can add here, I can add here, and now I can't add here, I can't add here, I can't add here, and then I can't add here or here because I'd have a blue pointing to an orange. And conversely, I want to flow down coloring blue. So these guys would have blue pointing to blue, so that's no good. Blue pointing to blue. This can't be blue because it would be blue pointing to orange. This can't be blue, but I guess this one can be blue. So hopefully I'm doing this right. And okay, there we go. So so this is how you do a flip. And now the theorem that we've all been waiting for. I apologize for all of that. I'm sure it was not very useful, but whatever. Here we are. So the theorem is that this actually defines a poset. So these flips actually define a poset, and these are the cover relations. So these flips are the cover relations. So here what I've done is I've drawn for you the Tamari lattice realized as an independence poset. So it really does define a partial ordering. And moreover, other things happen. If an independent set is a lattice, then it's a trim lattice. Okay, so we've perfectly captured the notion of a trim lattice as long as we were a lattice, but it doesn't have to be a lattice. It could be something else. It's more general. In fact, if you just start with any directed acyclic graph, then so you've oriented the graph, then you're going to get some interesting partial order on the independent sets of that graph. And so hidden behind the independent sets is a secret hiding independent set that you didn't see, but it's there and it's controlling the structure. Okay, that's the blue. Maybe you specify the blue. Well, there's a hidden yellow depending on the orientation, and it lets you create this interesting structure. It lets you generate them relatively efficiently as well. And so you have a trim lattice if the independence poset was a lattice. And because of work of Markowski, then we know that if it was a graded lattice, So a graded trim lattice is a distributive lattice. Okay, so this is roughly answering the question, what if a distributive lattice weren't even a lattice at all?
Yes, thank you, Nathan. Very nice talk. Very exciting. I guess I'll open it up to the audience. If there are any questions that people have, feel free to jump in.
Richard Stanley asks if you get a shelling of the order complex. I see, by the labeling. I see. So if you have a trim lattice, presumably if you look at, or even an extremal lattice, I don't know. Presumably that does. I don't know. If you were to use the, oh no, you need a trim lattice. I'm not sure, Richard. It's a really good question. If Hugh were around, I'm sure he'd be able to answer it.
Thank you.
I guess I was also wondering about maybe connections between trim lattice and other sort of lattice theoretic notions. Like, is this are trim lattices automatically semi-distributive, for example?
No, they're not. So Emily Barnard has work that's quite related, but doing it for semi-distributive lattices. And there, what she uses is she has a different map, a different way to associate join and meet irreducibles. And anytime you can do that, then you get some interesting sort of combinatorics coming out. So the edges pointing up, edges pointing down. You can do things like the Crevirous complement or row motion or whatever you want to call it. It's you're right. So you need some sort of bijection between the join and meet irreducibles to get that sort of going. Oh man. Yeah, Richard, I'm still thinking about your question. I'm wondering if it's not in Hugh's paper where he addresses EL shellability. I bet you he does talk about EL shellability there.
Yeah, I'll take a look. Thanks.
Yeah.
So Nathan, your examples of graphs, are these motivated by representation theory of quivers? Are the graphs that you come up with, are like Auslander-Wrighton quivers of certain algebras, or are these just sort of graphs that you came up with that seem to work nicely from something else?
Yes, I mean this example, right? This is this is the Tamari lattice. Is a special case of the Cambrian lattice. Hi, Nathan. And of course all of those are trim. So that fits into this framework. The particular labeling here, the particular graph that's underlying it, you can get this graph using the Auslander-Wrighton quiver, using the C sorting word for the long elements, stuff like this. Will your favorite tricks from Catalan combinatorics will get you this graph.
Nathan, can I ask a question? Can you relate the independence post set back to the original problem with antitrust suits in the post office and such?
Interesting.
From that?
Funny. I think you have trouble. So what can happen is, right, the length of the longest chain in an independence post set can get really, really long compared to the size of the underlying graph. So sort of, I guess the way to think about extremal lattices, they're just constrained in their height. Like they can get really, really fat. And trim lattices being extremal are also, they're constrained in how tall they can be. And here you can really explode upward. So you're asking if I can draw a similar picture, and this would be like, what is the relationship between the maximal orthogonal pairs and these tightness condition? And in our paper, we do show, so there are always, oh my gosh, hope I get it right. I think there are always more maximal orthogonal pairs. So if you happen, so if I give you a directed acyclic graph, on the one hand, that parametricizes, that could be thought of as parametricizing an extremal lattice. So you could make the maximal orthogonal pairs in there. And there are always more maximal orthogonal pairs, the Markowski construction, than there are this tightness condition that we came up with. So you get a map one way from the independence post sets to the to the extremal lattices. And I don't think, it can't be order preserving. Okay, hopefully that helps.
Yep.
Short answer, no.
Okay, any other questions for Nathan? Okay, well, if not, let's go ahead and thank Nathan again for a very nice talk.